measurements,
Precision.
versus accuracy, significant figures, and Dalton's atomic figure.
So I'm going to discuss the 7 basic units of measurements. First, kilograms to measure mass. Seconds to measure time. Kelvin to measure temperature. Ampere to measure electric current. And mole to measure the amount of substance. Candela to measure luminous intensity. And M to measure distance. So I'm going to discuss the 3 important units of measurements. First, kilograms. And second, Kelvin, including Celsius, Fahrenheit, and mole to measure the amount of substance. Kelvin have the same magnitude. The only difference between the scales is their starting point. So 0 Kelvin is the absolute zero, while 0 Celsius is the freezing point of water. Here are the conversions for temperature. With the given Fahrenheit, to solve for Celsius, subtract 32 from Fahrenheit and then multiply to 5 over 9. To compute for Fahrenheit, multiply 9 over 5 to Celsius plus 32 to compute for Fahrenheit. And to compute for Kelvin with the given Celsius, add 273.50. For conversion for mole, we need to know a special number, which is the Avogadro's number, equal to 6.022 times 10 raised to 23. To convert mole to number of particles, we need to multiply. We need to divide to 6.022 times 10 raised to 23. In order to get mole mass, we need to multiply the molar mass of the element.
Parenthesis numbers.
To convert mass to mole, we need to divide the molar mass of the element to get the mole.
In order to convert mole to particle, you need to multiply the mole by Avogadro's number. For example, how many atoms are there in 8 moles of potassium? That will be 8 moles of potassium times the quantity of the Avogadro's number all over 1 mole of potassium. That gives us 4.81 times 10 raised to 24 atoms.
Next, we're going to learn about precision and accuracy and how they differ from each other. So first is accuracy. Accuracy is a measure of how close your experimental measurements agree with known values. The closer your measurements are to the value, the more accurate the measurement. How does accuracy differ from precision?
We have already discussed accuracy, now let's define precision. Precision is a measure of how close your experimental measurements agree with one another. The closer your experimental measurements to one another, the more precise you are. In simple words, precision is more about the consistency of your experimental measurements.
Significant figures are important to show the precision of your answer. This is important in science and engineering because no measuring device can make a measurement 100% precision. Using significant figures allows the scientists to know how precise the answer is or how much uncertainty there is.
So now we will talk about the rules of significant figures. Rule number 1. All non-zero numbers are significant. For example, the number 32.2 has 3 significant figures because all of the digits present are non-zero.
So the next rule is zeros between 2 non-zero digits are significant.
2051 has 4 significant figures. The zero between a 2 and a 5.
Rule number 2. Leading zeros are not significant. They're nothing more than placeholders.
The number 0.54 has 2 significant figures. 0.0032 has also 2 significant figures. All of the zeros are leading.
There are 4 significant figures in 92.00. 92.00 is different from 92. A scientist who measures 92.00 milliliters knows his value to the nearest 1 over 100 milliliter. Meanwhile, his colleague who measured 92 milliliters only knows his value to the nearest 1 milliliter. It's important to understand that 0 denotes actual information just like any other number. You cannot tag on zeros that aren't.
Rule number 5. Trailing zeros in a whole number with a decimal shown are significant. Using a decimal at the end of a number is usually not done. By conversion, however, this decimal tree indicates a significant figure. For example,
540 indicates that the trailing zero is significant. There are 3 significant figures in this value.
Trailing zeros in whole number with no decimal, so are not significant.
Writing just 540 indicates that the zero is not significant, and there are only 2 significant figures in this value.
rule number 7. Exact number have an infinite number of significant figures. This rule applies to numbers that are definition.
For example, 1 meter is equal to 1.00 meters is equal to 1.0000 meters, etc.
So now, back to the example posed in the rounding tutorial.
Round 1000.3 to 4 significant figures. 1000.3 has 5 significant figures. The zeros are between non-zero digits 1 and 3. So by rule 2 above, they are significant. We need to drop the final 3 since 3 is less than 5. We leave the last zero alone. So 1000 is our 4 significant figure answer. From rule 5 and 6, we see that in order for the trailing zeros to count as significant, they must be followed by the decimal. Writing 1000 would give us only the significant figure.
So the last group is, for a number in scientific notation, n times 10 raised to x, all digits comprising n are significant by the first 6 rules. 10 and x are not significant. 5.02 times 10 raised to 4 has 3 significant figures. 5.02, 10 and 4 are not significant. Rule number 8 provides the opportunity to change the number of significant figures in the value by manipulating its form.
For example, let's try writing 1100
let's try writing 1100 by raising significant figures.
1100
By rule 6, 1100
It's 2 trailing
has 2
zeros are not
significant figures.
If we add
Its 2
a
trailing
decimal
zeros
to
are
the
not
end,
significant.
we have
If we add the decimal to the end, we have
4 significant figures by rule 5, but we're writing it in
1100
scientific
or
notation.
significant figures.
1.n times 10 raised to 3. We create a 3 significant figure value.
Next, we'll learn about John Dalton's atomic theory. First, content of John Dalton's atomic theory. Its elements are composed of smaller particles. That's what we call atoms. Next in John Dalton's atomic theory is all atoms of a given element are identical. So for example, we have an atom of tin. Their size, weight, and properties are all identical. It's only different if you have a tin and injury. Next in John Dalton's atomic theory is that a chemical reaction only involves separation, but not creation nor destruction. Next in John Dalton's atomic theory is compounds are composed of one or more atoms. Their ratio are integer or simple fractions. John Dalton's atomic theory are based on law of definite proportion and law of multiple proportion.